Okay, so today I'm going to talk to you about using Raspberry Pi for scalable device automation at the user level. So the same way a user would interact with the computer. So let me talk a little bit about the problem statement, right? So the core of the issue is that we have some operating system or device that we want to automate, but that device does not offer any sort of driver or API or anything we can interact with in software. And so this is a general problem. And then a way to think about this problem is to define it as in terms of requirements. So the requirements that we have is observe. So we need to be able to deduce the state of the application somehow from the device. We need to control. So we need to be able to send command and change the state of the application with our system. We need to be able to do this programmatically. So we want some sort of business logic or intelligence or AI, something that we will drive the rest of the stack. And then we want to scale. We want to do this in a way that's kind of cheap and efficient to scale so that we can tackle some hard problems. So at TestAI, I'll give you a couple examples that we had. The first one was a Chromebook device farm. So we have a contract with Google where we have to test a lot of applications on Chrome OS. And then in that specific instance, we have to handle things that are outside of the operating system slightly, like the login screen, the operating system updates, the reboots. We want these labs to be completely hands-free and remotely controllable, especially since the start of COVID, right? But there was no solution in the market for us to automate this fleet of Chromebook in a convenient way. And then we had the second problem, which is we had to test video games on Nintendo Switch or the Xbox, and we wanted to do it as well, completely programmatically, remotely, in a hands-free way. So based on these two problems, we came up with a solution using a Raspberry Pi. So you can see on the right what a Raspberry Pi looks like. It's a small form factor, it's the size of a wallet, basically. And then it's commodity hardware. So it's pretty cheap. Like one of those is like 100, 150 bucks, something like that. And so what we did is we customized this Raspberry Pi a little bit. The first thing that we did is add the HDMI capture card that you can see on the right there. It's called the B101 by Ovidea, and I'll have a reference at the end for that. But we put this HDMI capture card to basically capture the screen of the Chromebook and see the same thing a user would see. And then for control, we plugged a USB cable between the Raspberry Pi and the Chromebook, and then we use a feature of Linux that allows us to emulate some sort of USB device. And so we pretend for the Chromebook that we are a keyboard and a mouse. And then this way we can do the same thing the user can do, which is type and click around inside the operating system. To program, we exposed all the features that we have, like capturing the screen, controlling the mouse, controlling the keyboard. We expose that via some sort of web API. And then we have centralized control that is going to interact via the web API with the Raspberry Pi and control the devices. And then to scale it, basically, we created an image of the operating system. And then the Raspberry Pi is very convenient because you can use a SD card with the operating system in it, and it will just read from it and boot from it. So you can very easily swap out the version that you're using or which operating system and so forth. So with this solution in mind, let's talk a little bit about the first step, which is probably the hardest step, which is the HDMI capture. So the functional diagram is like this, right? We have a Chromebook, which has HDMI output. The HDMI output goes inside the B101 card. The B101 card is plugged into the CSI bridge of the Raspberry Pi. CSI is like one of those kind of plug that is on the motherboard of the Raspberry Pi, so it's inside the box. Then once you have this, we use a set of drivers called Video for Linux to basically show the device as /dev 1/video0. So it just shows up in Linux like any other video device. And then we pipe this video into a tool called GStreamer, which is a tool for manipulating video and audio feeds. It's a bit similar to FFmpeg, but it's more flexible. And so basically, the video goes into hardware encoding. So we use something called OMX H264, which is a hardware acceleration chip on the Raspberry Pi. And it's going to convert the feed from raw video into H264, which is the modern standard for video. And then we mux it, and then we can save it to a file, or we can stream it over the network. And so here's a few details, right? So when we declare the driver with video for Linux, we use something called an edit file. So basically, we want the Chromebook to think it's plugged into a screen. So the edit file is basically a device specification file in which we define which monitor it is, what is the resolution, and what is the frame rate. And so to do this, what we did is we ripped an edit file from a real monitor, which was an Asus monitor, if I recall correctly. And then we adapted a little bit the specification inside it so that it's exactly the right resolution for the OMX encoding chip, because they only accept a single resolution. And so basically, when you define this edit file and register the driver, Chromebook thinks there is an Asus monitor connected, and it starts sending the video feed over to HDMI. And then there is another interesting piece. It's like the way GStreamer works. So it's composed of multiple pipes that you chain together to create a multimedia pipeline. So here, we define the video for Linux as the source and which device it is. Then we convert it to a raw video feed. So XRAW means that it's basically uncompressed and unencoded. It's pure, media stream. And so it has this resolution of 1280 by 720 and a frame rate of 20 FPS. And then we pass it to the hardware encoder, to the muxer, which parses the stream and whatnot, and then saves it to file. So once you have this in place, what you can do is basically take screenshots, record videos, or stream the video. And so that's the first step of our system, which is observe. Then we can talk about the USB emulation part. So basically, in Linux, there's a way to make the Linux system act as if it was some sort of USB device. And the way it works is that you will have the USB link show up as a file descriptor on Linux, and you can basically write binary code onto the file descriptor, and it will be sent over the wire into the Chromebook. And then we use kind of a trick of the USB standard. There is a way to define arbitrary USB devices using the USB standard. And so in our case, what we did is we defined some sort of device that is a combined keyboard and mouse. So basically, the computer thinks it's one device that can do mouse movements and keyboard inputs. And then this is done using a language from the USB standard that you can see below. So this is not the whole file. This is just a snippet. But basically, you say something like, I want usage of X, Y, and wheel coordinates. And then you say this is sent by a mouse. And then you say the minimum of this value is minus 127, and the maximum is 127. And so basically, after that, you can send movement from the mouse into the wire into the Chromebook. Same thing with keyboard. You define usage for key character, and then you can basically send them over the wire. And then we also do something fun, which is do the same thing with the gamepad. So we used the Xbox gamepad. We looked at the report descriptor. We kept the part that was interesting. And then we could also control video games using the same methodology. Okay, so now there's a second subtlety about USB, using a USB device, the mouse specifically, is that the coordinates of the movement between the screen and the mouse don't match up. And the reason is that an operating system will have a lot of features like mouse speed, mouse acceleration, screen resolution. Sometimes there is accessibility that filters out the mouse movement and so forth. So you're never sure exactly what the pairing is going to be. And so you have to calibrate it. And so the way we calibrate it is that we run a full screen app on Chrome OS. It has a mouse listener. So whenever you click somewhere on the screen, the coordinate of that click in pixels are being saved. And so basically you move the mouse, to 0, 0, 0, 1, 0, 2, 0, 3, 1, 1, 1, 2, 1, 3, and so forth. And then you click every time. And then you basically create a lookup dictionary that allows you to say, I want to click at pixel 500, 750. And then the lookup dictionary will translate this into those arbitrary coordinates that the USB uses. And then you can decompose the movement into multiples of 127. So you do, 5 times 127 and then, 20 or something like that. And then once you have calibrated the system, you can basically say, click at this pixel coordinates. So that's kind of something to keep in mind if you want to do something like this. Okay, so basically this is what it looks like physically. So on the right side, you have the HDMI input inside at the top here. We also custom 3D printed the box for 2 reasons. The first one was for swag, right? We wanted to have the logo on there and then test AI and whatnot. But then the second reason is that the card is inside, the HDMI capture card is inside the box, but the default box is a little bit too small. So you need something a little bit bigger, like this one. And then you have the USB that you connect from this port here in blue into the computer. And so on the left side, we can see you have like the USB and the HDMI connected through an adapter and the USB adapter into the USB-C port of the Chromebooks. So the HDMI goes through USB-C, then HDMI, and then the USB goes through USB. So it's quite compact, as you can see. So it's pretty easy to basically put it on the side of the computer that you want to remote control. Okay, so then there's another aspect of the whole, managing a fleet, which is the quality of life, right? So we have HDMI and USB connected to the Chromebook, and then we have a web server with our API for automation and control, but we want to also have some sort of way to control the Raspberry Pi itself. So we basically designed a solution where we can do things like pull the code and restart the server with latest. So we can update the whole fleet, remotely in one line. We can restart the Raspberry Pi. We can deactivate or reactivate the HDMI input or the USB emulation. That is sometimes necessary if the host device goes to sleep or after a reboot, there is something weird going on. Sometimes we have to kind of turn it on and off back again to see if it's working, which generally works. We can grab the logs, and then we can also do something fun, which is take a screenshot of all the devices and make a big grid where we can see the state of all the devices at once. At the end of the day, it's really about what is convenient for your workflow and how do you want to manage your fleet of Raspberry Pi and Chromebooks or other devices. So this is a screenshot of the grid screenshot. So there, most of them are on the home screen. This one on the bottom right is on the login screen. This one on the top right has the menu bar open, so you can pick an app to launch. But imagine you can basically do this in real time and see what's going on over all the Chromebooks that you're managing. And the Chromebook is not even aware of it. It's just HDMI output for it. So to summarize, this is the functional diagram of the whole system. So we have a Chromebook. We have a hardware connection to a Raspberry Pi via USB and HDMI. And we have 2 sets of APIs. We have the automation, which is going to be for Chromebook, click and type, click with the mouse or type with the keyboard. If it's a video game, it's going to be press button and move joysticks, things like that. And then you have the fleet management API. Like I said, you can reboot, update, activate or deactivate, grab the logs. And then you have the centralized server to control the whole fleet. So, you've been watching this and you might have guessed there's something fun we can do once we can do, screen live stream, clicking and typing. And that feature is basically remote desktop, right? What we've done here is that we've built a poor man's KVM. KVM is a hardware solution for remote control of computers, and it's generally pretty expensive. So with this system, however, it's pretty cheap. It's like around $200, right? And so you can scale it easily. And then, so once you have this, our Raspberry Pi that acts as a KVM, what we did is we built a macOS app to control it. So we created a small UI using PyQt in Python. And then the GStreamer library inside this app will connect to the HDMI stream and show it inside the main window. And then it will display live. And then we've noticed the latency when we do this is around 200 and 300 milliseconds on the local network. And the reason is that we're doing hardware encoding of the stream. And that takes a little bit of time. It's not instantaneous. And then you have mouse listener on the screen, so you can click on the icons the same way you would click on any icon on your desktop, and you can type in the box and send keyboard events and whatnot. And so this system is basically, this app is generic enough that you can automate any sort of device that you have. So I have a screenshot of the app here. So you can see it's a macOS window. We have the screen of the Chromebook in the center, and then we can enter text at the bottom or shortcuts. And I also have a little video. So it's not very long. It's just to illustrate the features. So here I'm going to start the app on my terminal. So here you can see it was pretty quick. It connected to the HDMI stream in like a second or two or something like that. And you can see all the dashboard, right? And then I'm going to click on this Chrome icon here. That starts Chrome. And then I'm going to type, I click on the address bar. I type 123, press enter, it sends 123. And then I'm also going to input a keyboard shortcut here. So it's going to be left control and W, which is basically the screenshot in Chrome OS to close a window. And then I press enter and it closes the window. So you can see there's a little bit of latency, but for doing administrative tasks and debugging it's fine. It works fine. Okay, so let's go back to the demo. To the presentation. So summary of the tech stack, right? So for HDMI capture, we have the B101 chip by Ovidea. We use Video for Linux for the drivers. We use GStreamer for the streaming manipulation and the video manipulation. For USB elimination, we use the USB gadget feature of Linux. And then specifically for the Raspberry Pi, there's something called Raspbian, which is Raspberry Debian, which is a version of Linux. And then for the remote desktop app that I just showed you, we use the GStreamer library and PyQt in Python. Okay, and so I want to give you also a little bit of insight in Test AI. So we've built a platform for test automation using AI. And so the way it works is that it's visual. There's a way to make it work visual only, where it will do things like chop up elements like buttons and text boxes and whatnot on your screen. And then you can write test case and do everything visually using computer vision everywhere. And then because of this ability, we support platforms like, more computers, of course, iOS and Android, but we also do video game consoles like PS4, Xbox, and Switch specifically. And so, if you want to talk to us, we've used the Raspberry Pi in different contexts before. We've used it for automating Chrome OS, like I talked about. We used it for video game testing. And because you have a programmatic access to the device, you can do interesting stuff. So one thing we did, for instance, was measuring the latency between a video game input and the screen and the movement of the character on the screen using a video game streaming service. So if you have some sort of latency measurement, input measurement that you want to do, you can use the Raspberry Pi for that. We also automated Android phones on the sign-up screen. So before you can start Appium or anything like that, we can automate the first few screens of Android the first time you boot it. So you can create a user, define a password, connect to Wi-Fi, do all of this completely visually using our system. So if you're interested, talk to us, send me an email or reach out, and then we might have a solution for you. And then I want to thank the team. So in terms of leadership, Chris was, a great leader. He was enlightened and had the awesome idea to start this project. He had also very good insight into the whole thing. And then in terms of software engineering, it was developed by Alec and me. We both work at TestAI. And talk to us if you have some sort of problem related to our solution. Thank you for listening. And now we can move on to question and answers.
Thank you, Etienne. Please send your question through chat.
Okay, where is the chat? Yeah, I'm happy to go in details about the HDMI capture or the USB emulation if you have questions about that, because I think those are the hard parts. The rest of the thing you can probably figure it out by yourself. But